Hi folks, we're going to take a look at page 364, number 17. So here they tell us that a mass is being suspended by two strings. They give us the lengths and they tell us how far the strings are attached to the ceiling, presumably. And it says determine the tension in each of the strings. All right, so I'm going to start by drawing a diagram of what's going on. So I've got my ceiling, which we'll assume is horizontal. We've got our strings that are attached at two places. One string is longer than the other, so I'll try to draw it to make sure that we see that one's longer than the other. And then you've got a mass that's attached. All right, so this object here is not moving. So that means it's in equilibrium. So what does that mean? It means that whatever forces are acting on this object have to add up to zero. Okay, so let's try to see what forces are acting on the object. So pulling it upward are the forces in the two strings, what we call the tension in the string. So we got a force in that direction, a force in the direction of the other string, and then of course we have the force of gravity pulling it down. All right, and these three forces have to add up to zero. Okay, so if we wanted to try to draw a force diagram to help us solve this problem, well, we know that because there's three forces adding up to zero, it should create a triangle. So I'm going to start with, I think, the easiest force here, which is the force due to gravity. So going straight down, then I'll stick to the right-hand side of this diagram. So I've got this force going somewhere in this direction. And then I know that this other force is going to have to close off the triangle. Why? Because the object's not moving, meaning it's in equilibrium, meaning the forces add up to zero. So you end off where you started off. Okay, so let's see what information we have. Well, I know that the mass is 5 kilograms, so what that gives me is a way to calculate the magnitude of the force due to gravity. So the magnitude of the force due to gravity, so we'll call that Fg, okay, is just equal to 9.8 times the mass, because we're assuming that we're somewhere near the surface of the Earth, so the acceleration due to gravity is around 9.8. So 9.8 times 5 kilograms. Okay, actually that looks too much like 2 decimal places, so I'll draw it that way, and that's going to be 5, so that's going to be 49 newtons. Okay, clearly though, we need some other information. Okay, so I know I'm not going to be looking to be given the magnitudes of these forces, because that's what we're looking for. That's the tension in the string. So hopefully I'm going to find some angle information. But this is where you notice that they gave us some information, not about angles, but about the lengths of these strings. Okay, so we got the shorter string is 24, the longer string is 32, and then the distance that separates where they're attached is 40. Okay, but these vectors are in the directions of the string. So what I'd like to have is say, this angle here, so I can know the angle that this vector is going to be drawn at. And I would like to know this vector here similarly, so that I can, draw myself a little horizontal and get that angle. Okay, but because, again, we're assuming that this ceiling is horizontal, I've got these two parallel lines. Whatever angle this is going to be the same as the angle in the triangle, and similarly here. Okay, so while they didn't give us information about the forces, we're going to be able to use the lengths of these strings and the distance apart at the top to calculate these angles, which are going to allow us to get information in our force diagram. Okay, so it's a little indirect, but it'll do for us. All right. So let's say we start with theta. So theta is equal to cos inverse. So I know all three sides, so I'm going to have to use the cosine law. All right. So here, if I'm looking for theta, its opposite side is the 32. So 32 squared minus the square of the other two sides, minus 24 squared minus 40 squared, all over negative 2 times 24 times 40. All right. And let's calculate that angle here. Okay, so we've got cos inverse of, open a bracket in the numerator, 32 squared minus 24 squared minus 40 squared. Okay, and then divided by the denominator, negative 2 times 24 times 40. All right, and we get 53.1. All right, so now I'm going to do the same thing to find. So by the way, now I've got, this angle is 53.1, so it means this angle is 53.1, and already I'm going to have an angle inside my triangle. Okay, so let's see, 6 is going to be 30, looks like it's going to be 36.9. Okay, because these are complementary to each other because I've got a 90-degree angle. So now I'll do the same thing with phi. All right, I'm going to use cosine law again because, again, anytime I'm working with one angle and two sides, I'm always wary of using the sine law. So cosine law is almost as easy, so I'll use that one there. So here's phi, its opposite side is 24, so 24 squared minus 32 squared minus 40 squared, all over -2 times 32 times 40. And that gives us, okay, so cos inverse of, open the top bracket, 24 squared minus 32 squared minus 40 squared. And then open up a bracket for the bottom, -2 times 32 times 40. And that gives us 36.9. That's interesting. All right, so now I know that this angle here is 36.9. Okay, these two angles are the same because of my parallel lines. And this is why I said something interesting here, because when I add up 36.9 and 53.1, that gives me exactly 90 degrees. So this is, in fact, a right angle triangle. Okay, now not necessarily obvious right from the beginning, although if you think about it, take these three sides, 24, 32, and 40, and divide by, well, what's their lowest common denominator? Divide by 8, I get 3, 4, 5. So in fact, we could have seen right off the bat that it was a 90-degree triangle, would have saved us a bit of work, but I did want to sort of show that, you know, what you would do, because it's not always going to be a 90-degree triangle. All right, so now I have enough information to solve this problem. In fact, it's even a little easier because I can use right angle trigonometry. Okay, so if I call the tension in the 24 centimeter string, so I call that T1, so I'm looking for that magnitude, and I'm looking for the magnitude in the other string. And now we can calculate that, and we can do it with right angle trigonometry. So if I want to find magnitude of T1, well, for this angle here, that's the adjacent, and I know the hypotenuse, so I can use cos. So cos of 36.9 is equal to adjacent, which is magnitude of T1, over hypotenuse, which we found was 49. So magnitude of T1 is equal to, what do we have? We have 49 times cosine of 36.9. So that gives us 39.2 newtons. And now similarly for T2, okay, except this time I'm going to use sine because it's the opposite over the hypotenuse. So sine of 36.9 is equal to magnitude of T2 over 49. Okay, so magnitude of T2 is going to be equal to, just calculate that quickly, so 49 times sine of 36.9. Okay, 29.4. All right, so there we go. We have our two answers, our two tensions. All right, so let's just do a recap. So step number one was to figure out what was going on. Then we realized that we had an object that was not moving, so the sum of the forces, which I drew here, had to give me a closed triangle. And I used the fact that I knew the distances involved with these strings to help me find the missing angles, okay? And then from there, I was able to input that into my force diagram. Okay, turned out to be nice. It happened to be a 90-degree triangle. Don't necessarily assume it'll always be a 90-degree triangle. If it wasn't, then I'd be using sine law or cosine law here instead of basic trig ratios. Okay, that's it for this one.